All right, so in this video, we're going to go over those problems which you guys have a handout for. All right, so we take a look at reagents, and some reagents are only bases. Some reagents can be both bases and nucleophiles, but we're going to focus on writing things as elimination reactions only, right? So let's just go over then to, like, all the bases within here, right? So methanol, that's a weak base, right? So it has to be an E1 mechanism. Sodium ethoxide, that's a strong nucleophile, so it has to be an E2 mechanism, right? More of a strong base. It can also be a nucleophile. So actually, let me say, it's a strong base and a nucleophile. This is a strong base and also a nucleophile. So it could undergo both substitution and elimination. Sodium hydroxide is a strong base and nucleophile as well, right? So it could be both an E2 and an SN2. Now, sulfuric acid and heat, anytime we see heat, that right away means elimination. Okay? Elimination is favored at higher temperature. And this is weaker nucleophile, water, right? An acid in water. So it has to be an E1 mechanism. Okay. If you look at sodium amide, that's only a base. So if something is only a base, it has to be an E2 mechanism only. It cannot be E2 and SN2. In this case, you could have E2 and SN2, but this is tertiary, so it can only be E2, right? Things to keep in mind. Water is a weak nucleophile and a weak base, right? It's a weak nucleophile and a weak base, but we're really only writing elimination reactions in this case, so it's an E1. Sodium hydride is only a base, right? So that means it's an E2 mechanism. Butoxide is a base. It's a strong base. It prefers being a base than a nucleophile because it's bulky, so it's a bulky base. So if you think about it, that Regioselectivity applies where it favors the Hofmann product because it's a bulky base. You know that your final product has to be the Hofmann product. Hofmann is our major product. Okay, things to keep in mind. Now, in terms of substrate, as long as it's not a primary alcohol or a primary alkyl halide, it could be either E1 or E2 because primary alkyl halides and primary alcohols do not undergo E1. Okay? So, we'll start with the first one. You know, you have methanol, you have the chlorine, it's tertiary. You take a look at the 3 carbons, 1 bond away from the carbon directly attached to the leaving group. Those are our beta carbons, but we're using weaker. As long as they have hydrogens attached to it, right, we could actually draw the mechanism. Okay, but I'm going to do the products for all, and then we'll go through the mechanism if we have time. All right, so if this particular beta proton deprotonates, we form a pi bond right here. Now, if that particular proton deprotonates, we form a pi bond right there. But those two are really the same. They're identical. All right, if this proton deprotonates, then we form a product like this, right? So if you think about it, those are more substituted alkene, and this is a less substituted alkene. This is not a bulky base. So the major product would be the more substituted alkene, right? Or what we call the Zaitsev product. And the less substituted alkene is the minor product in this case. Okay, what if we have sodium ethoxide? Well, this is a tertiary alkyl halide, so it cannot actually undergo SN2 mechanism because it's tertiary. It can only undergo E2 mechanism, right? And you look at the carbons 1 bond away from the leaving group. Those are the carbons that have a hydrogen where elimination can take place. So redraw the product, redraw the substrate exactly how it looks. Get rid of your leaving group, right? Everything else remains. And then add your new pi bond. That would be 1 product This would be another product, right? If this proton was eliminated. And this would be a third product. Those two, however, are exactly the same. You have a methyl off of this carbon, so those two are actually exactly the same. So there's only two products in this case and two products in that case. Well, this is not a bulky base, so the Zaitsev product would be our major product, all right? This would be our major product, or what we call our Zaitsev product. Okay, and the mechanism for that is simple because it's an SN2, right? The base, so ethoxide, so we have the oxygen that is negative, oopsie. The oxygen that is negatively charged, it's going to go in, it's going to deprotonate, those two electrons are going to go right there, and a pi bond is formed and the loss of a leaving group, and then we get our major product. All right, well, what about in this case? You look at the carbon attached to the leaving group, there's a hydrogen right here. You take a look at this carbon, well, this carbon has 1, 2, 3, 4 bonds, so it doesn't have any beta hydrogens, so the only possible position would be right there. So the only possible product in this case would be get rid of the leaving group and add a pi bond, as long as this carbon has a hydrogen, right? So that would be the product. This carbon doesn't have any beta hydrogens, right? So there's only one possible product. This was not a bulky base, but that's the only product, right? And if you were to draw the mechanism, the base deprotonates, you show the formation of a pi bond where those two electrons are the two electrons that form the pi bond, and we have the loss of a leaving group, right? If we have concentrated sulfuric acid, we drew the mechanism a little bit ago, but here's again the carbon directly attached to the leaving group. You look one carbon away, this carbon has a hydrogen, right? So either one of those two, so we can end up forming two different products. Get rid of the leaving group, and here's the less substituted alkene, the Hoffman product, or you can have the more substituted alkene, which is the Zaitsev product. And because we're not using a bulky base, this would be the major product, and that would be the minor product. Well, what if we're using tert butoxide, right? This is very similar to this example, except now we're using a bulky base, so the major product is our less substituted alkene, right, at this carbon-carbon bond. And if you were to draw the mechanism, tert butoxide, it's going to go in, it's going to deprotonate, a pi bond is formed, and we have a loss of a leaving group. Very simple, right? Sodium hydride is not a bulky base. So there's a hydrogen right here. That hydrogen is beta to the leaving group. There's a hydrogen right there as well, right? There's only two carbons that are in a beta position to the leaving group. So the two possible products would be one, the major product, the more substituted the alkene, or the minor product, right? Where now it's between this carbon-carbon bond, right? But it will always involve the carbon that was directly attached to the leaving group and one bond away. All right, what if you wanted to draw the mechanism? Well, this is a hydride, sodium hydride. So what we have is a hydrogen with two electrons. That's the one time where the arrow can start from the hydrogen because it's a hydride. It's going to go in, take a proton. Those two electrons are going to go to form a pi bond, and then we have the loss of a leaving group. And that would be our major product, or our Zaitsev product, right? Well, in this case, it's water, so it's a weaker nucleophile. It's much like an E1 mechanism, okay? Again, that's the carbon directly attached to the leaving group, one bond away. There is no hydrogen here. This carbon has 1, 2, 3, 4, so that's really the only possible position for it to form. Okay, draw everything exactly how it looks. Just get rid of the leaving group and decide where the pi bond was going to form, and here's a new pi bond. Okay, so that's the only product. So what about in this case? Well, this carbon is attached to the leaving group. one carbon away, this carbon has 4 bonds, it doesn't have any hydrogens. This is the only one that actually has a hydrogen. So if you think about the mechanism, it's a strong nucleophile, so it's much like an E2 mechanism, right? The base takes a proton, we have the loss of a leaving group, and those 2 electrons go in to form a pi bond. Well, there was already a pi bond. Well, that's when you have a triple bond. So that's exactly when we form a triple bond, okay? So we had 1, 2, 3, 4, 5 carbons. 1, 2, 3, 4, 5 carbons. 1, 2, 3, we had 2 methyls. 1, 2, 3, we had our 2 methyls. Those are our 2 methyls. Notice when we have a triple bond, this is a carbon and this is a carbon. Those are those 2 carbons, right? Ends up being as a line. We're going to look at that at a later chapter. So we can form alkenes or alkynes when we do elimination reactions. All right, I hope that was helpful. Practice E1 mechanism. Watch the other video if you didn't quite get E1 mechanism, and I will see you later.